Today, I am on the lands of the Kulin Nation here at Monash University, Clayton, and I know that RMIT, where our guest is from, rests on the lands of the Wurundjeri people of the Kulin Nations. And we've got a number of people online as well. So wherever you are, we wish to respectfully recognize the traditional owners of the lands on which you are sitting and recognize their elders past, present, and emerging. Welcome to another Talk2D event hosted by AM2D, the ARC Research Hub for Advanced Manufacturing with 2D Materials. And I hope you enjoyed the talk. Just before we get on to the talk part, I just want to say that I'll just check to make sure that the comments... that's an AI thing, fair enough. I just want to say, please have a look on LinkedIn and follow our page, ARC_AM2D. We advertise a number of events up on that page. And also for those of you in the room and also online, just reach out to me afterwards and I can add you to our mailing list as well. So again, we're hosting a bunch of events this year and we'd love you to be part of those events. I'll do a quick introduction of our speaker. Dr. Irfan Haider Abidi is a materials engineer by training and received his PhD in chemical and biomolecular engineering nanotechnology from the Hong Kong University of Science and Technology. He was a research fellow at the Centre for Advanced 2D Materials, National University of Singapore from 2018 to 2021. And is currently a research fellow in the School of Engineering at RMIT University. Dr. Abidi's research focuses on atomic scale engineering of 2D materials using scalable manufacturing techniques such as CVD, and his work targets applications in electronic, optoelectronic, quantum, energy, and electrochemical devices. He has co-authored over 45 high-impact journal publications, received 3,000 citations, and holds 4 US patents and is the editor of 1 book. Dr. Abidi has secured over $3 million in competitive research funding as a CI, including a discovery project and a LEAF grant. And as a lead investigator, he has also won 2 consecutive Australia Economic Accelerator AEA Ignite grants, securing $900,000 across 2 funding rounds. Once again, I hope you enjoyed the talk today, and I'd like to pass over to our guest.
Thank you. Thanks, Phil, for the introduction. It's a long one, but thanks very much. And thanks to everyone for coming and joining me for this seminar. I'm very excited to share my research with you, which I've been doing for the last maybe a decade. I will talk through some atomic scale engineering of 2D materials, which mostly on the like monolayer materials, and how we can engineer those materials for different applications. So I will go through this. Yeah. So this is a journey for me, traveling around from starting from my PhD, which I did from Hong Kong University of Science and Technology. It's a very beautiful campus, and it's still, I think, one of the most beautiful one. And then I moved to Singapore for my first postdoc at National University of Singapore, where I worked at the Center for Advanced 2D Materials, which is one of the leading center for graphene and 2D materials. Then in 2022, I moved to Australia. I started working at RMIT with Professor Sumit Walia and the Center for Opto-electronic Materials and Sensors. I travel along, but I also travel along the landscape of atomic materials through atomic scale engineering. And I had one thing common, toolbox, which was CVD with me all along the way. So which I used to play with the materials. Very brief introduction of 2D-dimensional material. We all know that, but I want to acknowledge these 2 gentlemen over here who started this field in 2004 for the first time, once they exfoliated graphene, which is pretty much simple way using a scotch tape, and they exfoliate a graphite. Some one layer of graphite, which becomes graphene. And since then, a lot of work has been done for last 20 or so years, and we came to know outstanding properties from graphene in terms of mechanical, electrical, thermal, and all thermal properties all around. And the most astonishing one for the graphene was electronic properties, because it gives a very unique electronic distributions on its structure, which is a kind of zero band gap, which is very unique and different. It's not like not a connector, not a semiconductor, something unique material. Of course, since then, a lot of research has been done, and at the moment, we have a family of 2D materials, maybe hundreds and thousands of combinations. Now we have, and it's all starting from the connecting to semiconductors to insulating materials, and then we can play with around to make some heterostructures of different materials to even further enhance their capability. We can see over this plot here, you can see if we have from zero band gap from graphene to the mid band gap are maybe semiconductors, and then all the way to boron nitride, which is one of the insulating 2D materials. So this all materials come together and open up a lot of prospects and the different applications. So since the start of this field, the first exfoliation of graphene, there are a lot of expectations from these materials. If we talk about specifically for electronic application, electronic devices, as we are moving towards technology which is going to be miniaturized every second day, and once we move beyond the Moore's law, we have to shrink down further the devices sizes. And what is expected that these 2D material can do wonders if we can combine them with the current CMOS technologies. We can even further go down to next like future technologies for quantum computing or neuromorphic computing. So these 2D materials become most and most important over the like along the time and also in the future. Other than like electronic devices, there are also a lot of applications for these 2D materials in biosensing. Like one of the example over here is in the COVID time, some people have done like graphene FET for using this graphene FET for the detection of the COVID virus. And also in the energy, we all know we can use graphene, and also a lot of electronic and gadgets are all required these 2D materials, future devices. However, we have a lot of expectations from these materials, but to fulfill those expectations, the most important thing is how we synthesize them or how we manufacture them on a larger scale, so that we can really harvest all the benefits from these materials. So there are a lot of different methods to synthesize these material. Mainly we can divide into two types. One is top-down approach, and one is the bottom-up approach. For the top-down approach, it's like mechanical exfoliation, which is the most fundamental one, but that's only restricts to the fundamental studies. It cannot be used for the like application and everything. Then the most worth mentioning is liquid phase exfoliation method that is used for preparation in like energy applications and a lot of applications. That's very common method. And if you talk about bottom-up approaches, that's more about atomically. You have to stitch them together to make a films and make layers. So that's the most feasible one, and most common one is the chemical vapor deposition. So we can also, if we scale them on the quality and the price, we can see basically liquid exfoliation one is in terms of price is very compatible. But in terms of quality, if we talk about, we want to really control on the structure of the monolayers in terms of atomically defects, and also we want to have a very high quality one. Then we have to move towards bottom-up techniques like CVD or MOCVDs or MBEs. But in terms of price, a little bit, these techniques become a little expensive, but you have to trade off between the quality and the price. So CVD is a well acceptable technique in terms of if you talk about applications where the quality is the most important thing. So here again, I just put all the different methods and different applications. So if you move on that side, if you want high crystal quality or homogeneous thickness for applications in electronics, optoelectronics, or spintronics, for that case, you need this kind of chemical vapor deposition or molecular beam epitaxy kind of approaches. And if you want high surface areas like in the energy of supercapacitor applications and hydrogen evolution catalysis, their quality of the crystal is not that critical. There you can use other methods like liquid exfoliation or wet chemical synthesis methods. So I was most toward the chemical vapor deposition because I've targeted more electronic and optoelectronic applications. So this is just a very simple schematic to show how the chemical vapor deposition works for the growth of graphene. So normally you have one catalyst, which is here the copper. It could be nickel. It could be other metals, and then you put it at in a CVD furnace, a CVD tube, and then you have high temperature, and then some of the precursors, like in here, you see the methane gas is coming in. You can use acetylene, other carbon precursors can be used. And those precursors at high temperature dissociates on the surface of a catalyst, which is copper, and it gives you ultimately a layer of graphene, which is basically carbon, sp2 bonded carbon sheet. Of course, there are different steps for the graphene growth. First is adsorption, and then once absorbed, it dissociates, removes this hydrogen. So that step is called dehydrogenation. And then there's a surface diffusion for the carbon species, and ultimately they stitch together to form a continuous sheet on the surface of a copper. So that's a very fundamentally how CVD works for graphene growth. And now over the time also CVD has been evolved for the fabrication of the different 2D materials, and especially we can now grow single crystals to continuous films. Also, we can use this technique to grow heterostructures, and ultimately we target what kind of device application we want. So based on that, we can engineer the materials within this CVD technique. There are different parameters which we have to control. It looks easy, but it has a lot of different things and combinations to set a recipe to grow high quality films. So we all have to take control of pressure, temperature, and what kind of substrate you are using. There are different kind of gases you have to involve, and all of them come together to give you a perfect high quality kind of films you want for different applications. So where I contributed to this field, so there are a lot of challenges in the CVD growth of graphene. So one of the challenges was basically, you see over here, if this is the optical image of a monolayer graphene, single layer graphene. But within the single layer, you can see there are small these patches, which are basically multi-layer patches. But for the application, you want it to be very uniform single layer graphene. You don't want to have small patches because this makes the film quality non-uniform that can hurt your device performance. And the second important thing is in graphene growth is we want to do a single crystal one. We don't want to make a polycrystalline, because once you're a polycrystalline graphene, then again, the grain boundaries act as scattering sites. It can affect the electronic performance as well as optical properties. So these two challenges are very important. One is to get the single layer graphene exclusively, and second, to avoid any kind of grain boundaries to grow single crystal graphene. So people think about the graphene growth as a top surface based mechanism. So basically what we have in the CVD, we have a copper foil, and the copper foil you have two sides, top and back. So people only mostly in that literature, they care about like how graphene is going on the top surface. So like you see in here, so carbon source coming from the top, and it deposit or absorb on the surface of copper. And then once we have one layer, you can have second layer underneath the first layer, something like that. Okay. So in this way, we can end up with a growing like multi-layer graphene. We have top layer of graphene, and then you have bottom layer as a bilayer of graphene. However, I did a very control experiment to see whether only top surface matters in the CVD growth and the bottom surface of copper foil also matters. So I just did a very controlled experiment in which I have two different kind of configuration in my experiment. In the first one, I just put simple like usually we do during graphene growth. So we put copper foil on a quartz substrate and put inside this CVD furnace. Another one, I just wrap the copper foil so that only top surface is coming into play during the reaction, and the backside of the copper foil is not coming into reactions. So what happened? It was very stark contrast. You can see once in the open kind of configuration we grow, we see the bottom layer is of course a monolayer graphene, and then you have a lot of these multi-layer patches. But once we do this like closed wrapped kind of configuration, we can only see it's a completely single layer graphene. So this control experiment gives us one clue that actually there's something happening at the backside of the copper, which also take part on the top side of growth. So to make it more sophisticated kind of growth experiment, now I put it copper onto different types of substrate. One is just I put it in quartz, like in a quartz tube, and one I put it on the nickel. So when I put this copper foil on a nickel and then I grow inside the tube, I can see once I put it on the copper on the quartz, it gives me like again single layer graphene along with a lot of multi-layer patches. But once I put it copper on the nickel, I can see only clean single layer graphene I can grow with this kind of configuration at the bottom. And on the larger area like this, at this time 2 by 2 centimeters square, you can see it's completely single layer graphene without any patches. So that nickel did some magic at the backside, which I call it a gettering phenomena. So the gettering phenomena is very common, I think, in material science language. So I use nickel as a gettering metal at the backside of the copper. No, gettering. So getter metal, something like that. So
Can you explain that? I know a little bit, but
yeah.
for our own education, what is
so gettering is basically something a sacrificial metals, you can say. So you have two metal. So one gettering is just eat away all the environment in the like carbon or something, any other thing. It just remove all this kind of.
Why copper doesn't do that?
So copper has a first thing is copper has a solubility limit of carbon.
I know.
Yeah.
This one.
Yeah.
Thank you.
And
Yeah.
so I just explain here a little bit more in schematics, kind of cartoons. So in this kind of first growth, we have once copper on top of quartz. Some of the carbon from the backside can diffuse through and get to the top. And then you get
Often carbon diffuse through copper because it has very, very little solubility. But carbon doesn't diffuse into copper.
But at 1000 degrees Celsius, the solubility is a little bit higher as compared to the room temperature.
Okay.
Yeah.
Good.
So, so at this, and then the copper foil, so then it creates a lot of multi-layers, and also because once you have more carbon everywhere, it also creates a lot of nucleation sites. So you have more nucleus of graphene. So we have high nucleation density of the graphene crystals as well. But once we put it on the nickel copper, then because on the backside, all the carbon is getting into the nickel, so it's not going up. So we are having mostly on the top single layer of graphene one. And second, we are also getting more large size because we're controlling nucleation density on the top as well. So this phenomena was very, it actually happened accidentally with me also, but it was very useful. So we grow this using this method. Of course, single crystal in here, I want to make mention like there are other methods also as well to control the nucleation density in a single crystal graphene growth, for example, the top and bottom. The difference is you have to use some sort of seeding growth, so to have only few nuclei of the single crystals. And then one paper, the first paper on the single crystal graphene was, in that case, they use some oxygen environment to control the nucleation density of the graphene. But using with my this gettering approach, we were able to control the nucleation density. For example, on the top left corner, you see a lot of hexagons are there, so nucleation density was quite high. At the same time, the same kind of area, you have only one nuclei sitting in the middle for the single crystal graphene. So using this kind of method, you can control the nucleation density, and also you can control the formation of bilayer unwanted patches in the graphene. So you can have very nice single layer and also single crystal. At that time, I was able to make one hexagons around like 0.6 millimeter. At that time, it was very nice. Now, of course, people have gone beyond that. So this kind of growth help us to improve the quality of graphene in terms of electronic properties. Mobility has improved, and also optically, the scattered centers have removed. So optically also a little bit enhanced in terms of properties. Then we also use this method to maybe do the pattern of graphene. So in this, for example, image, you can see I put a one nickel mask, which I have written something on top of it. This is my university name. And after the growth, you can mask it. So basically, you can see over here on the copper, you have only graphene sitting on where you have the mask. So everywhere where nickel is masking the copper foil, it will not let graphene growth. So this is one of the very initial studies that I started with. And then some people also followed it using this gating method to grow other 2D materials like MOS2. So this is the one group from the NUS. So they started also growing using this method to grow say large single crystals of MOS2 using a similar method. Like that was to control, if you want to control the nuclei of a single nuclei. Otherwise, now there are also other techniques to grow single crystal graphene by controlling the orientation of the crystals. So if you can control the orientation of the surface on the single directions, then once these individual crystals, which are actually oriented on the same angle, once they come into connect to each other, they're stitched together to make a whole film a single crystal of graphene. So this method is also very interesting and can be used to grow single crystal graphene on the larger area. So now I move to the second topic of my presentation, which is that was for the single crystal, completely perfect. Then I realized let's put some defects in it. It's more perfect and maybe sometimes not that required. So in this case, I realized sometimes atomic defects actually can change the properties of the material, especially because we are playing with just one atom thick of material or three atoms of thickness of material. So these defects can really change the properties, and actually you can modulate the properties what you want from the different materials. For example, in this one, so usually, for example, in this case, we have MOS2, which is the semi-reacting material, semi-reacting 2D material. In that one, if you react some vacancies in the MOS2, for example, sulfur vacancies, it can change optical properties. Like in that case, so you can see in the top left corner, we have photoluminescence that will change, and also electronic properties changes once you have more vacancies in the MOS2 on the fiber surface. You can see there some sulfur is removed from the layer. It will change the connectivity and also the properties. And you can also retain these properties again if you do some surface treatment. For example, if you have some surface defects, you can do some chemical treatment. It will retain its surface again, and your properties will retain again. So this is very interesting because you have just a one layer of material, so it can be easily manipulated using different techniques of defects formation and also like passivation. Another very common defects are in boron nitride. They are used because boron nitride is a wide bandgap material, 2D material. So we can have some in-between in-gap states which can act as a quantum emitters. So this field also has been a lot of papers have been published in this field as well. So, but normally, whatever the defect formation techniques are available in for this monolayer 2D materials, they are mostly two steps. Like we need to do this in the post-synthesis part. So first we have material, and then we do the defect formation, maybe through ion implantation or through electron beam irradiations. So these kind of two-step processes we can use to create some defects in the material. But these defects, these kind of techniques are more like they're not very controllable. You can see you can create even some voids within material, or maybe the materials become not already break or something. So it's not what you would want to have very controlled atomic defects. So this can be done with the CVD itself as well. So I use CVD again as a tool to control, to create some defects in the materials. So first example I used here I used the same gettering CVD method to grow boron nitride. So principally the mechanism is the same, because in this case, again, we are using copper foil, and on the copper foil, we are using boron nitride growth. So once we do, again, with two different types of substrates, the defects in the boron nitride was changing. Actually, we can see here over here, like this is the PL emission spectrum image of the boron nitride growth, two different growth conditions. Once we have a gettered growth, in that case, we have less quantum emitters, and we can also change the position of the emission during this control based on the defects control in the boron nitride.
What's the purpose of copper substrate here? What role does it play?
For the copper substrate?
Yeah, why you need copper substrate?
So boron nitride also grows similarly like graphene. So it requires a copper as a catalyst.
Yeah, also catalyst.
Yes, yes.
Thank you.
Yes.
Yeah, thanks.
So again, we use copper as a catalyst, and then we grow boron nitride, and then you can transfer to any substrate you want. Yeah. So a little bit introduction about MOS2, I think you already know. So basically, again, second most studied 2D material after graphene. So it has been used for different applications, especially optoelectronic materials, optoelectronic applications. So I use the same CVD method to in situ control the defects in the MOS2. So you can see over here. So I use two different types of growth conditions. One is called APCVD, which is atmospheric pressure CVD. Another one I use low pressure CVD. So in atmospheric pressure CVD, basically you have oxygen environment. Basically you have oxygen in the environment, so that can play role into the growth. And the second one, I use low pressure CVD, where I remove all the oxygen within the system. So basically oxygen deficient condition, a deficient kind of condition in the growth. So if you see optically in the top two images, these two images, you can see it's very much similar kind of triangle single crystals of MOS2. In terms of AFM also, like you can see, it's a single layer, the thickness is kind of similar. But once you go to the atomic level, you can see there are more defects in which I use conditions of low pressure CVD conditions. But in terms of once we use APCVD, the defects are lower. So this is interesting happening once we just change the conditions of the growth. So once we do some more characterization to see what these defects can do, so we can see, especially in terms of photoluminescence emission, you can see for one type of growth gives very high photoluminescence, another one gives very low. So the same MOS2, single crystal MOS2, in one case you see the photoluminescence is like 60,000 pounds at the same parameters. Other MOS2 is giving you like 200. So the photoluminescence is completely gone. So what happened once we grow with the low pressure CVD technique, or low pressure CVD, actually we are actually creating some sulfur vacancies in the MOS2. So some of the sulfur vacancies are removing during the growth. But if we have an oxygen-rich condition like APCVD conditions, those sulfur vacancies will immediately passivate with oxygen. So this is the two different types of growth conditions. So if you have only low pressure CVD, there are sulfur vacancies which are created, and they will retain itself. So then you will have this kind of properties. If you have oxygen in the environment, like oxygen passivation in the atmospheric pressure CVD condition, in that case, because the sulfur vacancies are passivated with oxygen, so it's kind of similar behavior, which very kind of ideally MOS2 should look like. However, like defects, if you want oxygen passivated one MOS2, or if you want a sulfur vacancy MOS2, both of them their own characteristics, and both of them can be used for different purposes. For example, in here, low pressure CVD, which has a sulfur vacancy in it, it shows very high photocurrent as compared to that purple color curve there. So in that case, once you have atmospheric pressure grown MOS2, which has oxygen passivation in it, in that case, the photo response is like lower down. And but similarly, in terms of their behavior, once we do this photo optoelectronic properties testing, we can see it's the fast response in the case of oxygen passivated MOS2. But once you have a sulfur vacancies, the decay is very long. So this decay can be useful in different applications in the devices. Then we all know that these defects in 2D materials are useful in catalysis application as well. So with the collaboration with Dr. Cameron in Monash in chemistry department, so I contacted him. So we want to study because he has this very nice SECCM technique, which can map over the area of to map the defects on the 2D materials. So I give this grown low pressure CVD grown MOS2, which has sulfur defects in it. So you want to map it. There are like globally people do in the HER testing, they can find out, but they cannot map it. So in this case, because we have the sulfur vacancies defects sitting on the surface in 2D maps, and we can clearly see once we have defected MOS2, we can hide amount of these activation sites or active sites on the surface of MOS2 for HER activity. This is also useful. So in this case, sulfur vacancies, we have to passivate if we want to get it into the piezoelectric properties of MOS2. So for this case, what we observe that once we have we passivate these sulfur vacancies with oxygen, the piezoelectricity enhances. That is because of once you have a sulfur vacancies, you have the surface is more charged, electrically charged. It's basically n-doped surface. But once we dampen them with the passivation of the oxygen, then the piezoelectric coefficient will enhance like 2 times for the MOS2. So this was we used for one of our project with AEA. So we use MOS2 into the paint matrix, and this composite used as a like piezoelectric paint or piezoelectric coatings. We can generate harvest energy from it, and also for the like smart structures, and we can have this kind of application. We can use this piezoelectric paints. We can grow MOS2 on the larger area like wafer scale. So here you have a photograph of one of the half-cut sapphire wafer. So it's quite uniform over the large area. MOS2, we can also grow other 2D materials like WS2. So in that case, you can see over here, it's similarly, we can use low pressure CVD growth for the WS2. Also, we can use atmospheric pressure based WS2 material. So basically, just an example, like we can have different TMDs for different applications, MOS2, WS2, and also the heterostructures of these material. So there's another interesting interfacial engineering we can do in the CVD. For example, we have 2 layers of MOS2. We can have different stacking of 2 layers. So for example, in the image you can see if you have a monolayer MOS2, one single crystal, and then if you have another bilayer on top of it, so 2 triangles sitting on top of it on the same angle, it's becomes 0 degree or 3R bilayer, and then we can also have a 360 degree, so it's rotated like 60 degree 3D symmetry. So in that case, you have a 2H bilayer MOS2. So we can control with the conditions. You can grow different stacking of the bilayer MOS2, and they have different properties once you have 2 different types of bilayers MOS2. For example, 2H and 3R. In our case, 2H gives us higher photo response as compared to the 3R, and which is because of the interlayer coupling between the 2 layers. Once you have a 2H phase of bilayer MOS2, we have higher interlayer coupling, which actually enhance the overall response in the optoelectronic properties. Again, we did with the collaboration with Cameron, we did HER applications and HER visualization. So in that case, it's interestingly, we again see if we just change the stacking of 2 different bilayers, the activity of the HER is changing. So in our case, we see in 2H MOS2, which is like a 60 degree rotated bilayer. In that case, we see higher activity as compared to the one in which we have a 0 degree rotated bilayer MOS2. Then we use MOS2 to grow another 2D material on top of it, which is sometimes, in this case, we grow SB2S3. SB2S3 is a 1D material, and it's normally hard to grow in 2D lateral direction. So in this case, we use MOS2 as a template, which is a van der Waals. It has a van der Waals surfaces. So this van der Waals surfaces attracts another layer on top of it. So it will grow the second layer on top of it in the 2D form as well. So using this method, which we call van der Waals template assisted growth, we were able to grow exactly like copying the bottom template MOS2 on top of it. We have SP2, S3. These ramen suggest also the formation of 2D SP2, S3 film on top of single crystal MOS2. The beautiful images are coming from the top sims. So basically, we have heterostructures. We want to see how uniform is your heterostructure on top formed during the CVD. So you can see on top, before any sputtering, we have on the surface only SP2, S3. Once you remove it using top sims, we can have bottom layer MOS2, and once you remove MOS2, you have silicon oxide. Also, you can see on the vertical distribution of different ions using top sims technique, which we collaborate with the HKUST University in Hong Kong to get these top sims 3D images. So we wanted to understand like why MOS2 helps to grow these two different 2D materials on top of it. So we did some DFT calculations. So in that calculations, we realized that MOS2 actually lower down the diffusion barrier of the second material on top of it, which means once this heat is absorbed on the MOS2, it can just diffuse on the surface. Once it diffuses on the surface, it easily can make 2D films. Otherwise, if it cannot absorb on the surface, it will become 3D or 3D particles or 1D particles. So it will not make 2D lateral diffusion. So MOS2 will give that kind of leverage to grow in the form of 2D lateral structure of SP2, S3. So this is not just SP2, S3. You can also grow other 2D materials on top of it using the same phenomena of this van der Waals template assisted growth. So at a heterostructure, once we tested these heterostructures, it actually enhanced the most important thing is the broadband. It's optoelectronic detection. For example, it can MOS2 itself is just active until 660 in the visible range. But once we have a heterostructure with SP2, S3, it also responding to the higher wavelengths like into IR, near IR and IR 1050 nanometers. So I think, yeah, so I will come to the last part of my talk, which is the completely random structure, like from single crystalline to defects. And now we move to the completely disordered structure, again, it's amorphous structure. So there, of course, there are pros and cons once we want to get crystalline materials. But one of the biggest issue with the crystalline materials are, if you want to get crystalline material, graphene, and high quality one, you have to go with high temperature. Like for CVD, you see for graphene, we have to use 1000 degrees Celsius or minimum 700 or 800 degrees Celsius temperature required. Also, sometimes CVD processes are quite longer and also require catalytic substrates. And also in the end, because all the growth is happening on the copper, we have to ultimately transfer to the required substrate, for example, membranes, for example, silicon oxide or other substrate you have to ultimately transfer. And that transfer will generate a lot of defects and everything. And also in the terms of processing, because this temperature is very high as compared to CMOS processes, which are mostly below 450 degrees Celsius. So making crystalline material is always on the expense of high temperature. Is very it's a big challenge to translate into the industry. So there's another. So that's where the other way around we can think of other material because we already have from crystalline 3D to amorphous 3D, but we didn't have much on the amorphous 2D materials. So while we keep the main properties of 2D materials like atomically thin, freestanding, transparent, surface area, all these properties intact of 2D materials, we have to lose a little bit of crystallinity. So if we have a 2D amorphous material, we still can get all these properties, but just the crystallinity will be, we have to.
What about the electrical properties? Amorphous materials, you mentioned that.
Yeah.
That
It depends, like how you say decline. If you want dielectric properties, it will enhance. So it's reverse. So basically, conductivity will decrease, but that's other way around. It will become more important material. Yes, yes. So that's like how where you want to put it ultimately. So in terms of, like, for example, in membranes, you don't need electrical connectivity or crystallinity is not that much important. Other things are more important. So there have been some, like, again, some work have been done previously to achieve amorphous materials, but they are not really amorphous. They are basically nanocrystalline either. You also have maybe disorder or defected graphene once you are using these different techniques. But what my group in Singapore, where we have achieved, actually for the first time, we have one freestanding monolayer, completely monolayer amorphous carbon. That was in 2020. So it's completely sp2 carbon. It's not like 3D amorphous, which is basically sp3 bonds, carbon bonded carbon. So it is a single layer and sp2 bonded carbon and can be grown on larger area. And you can see this mech is just floating on the top of the water without any polymer support. Normally for graphene growth, you need some support to transfer. So that means it's quite strong enough to sustain its structure as well. So more like into the structure of what is the difference between graphene and meth, you can see on the top corner also. So graphene is more regular hexagonal carbon rings, but in meth you have a very wide distribution of the bond length and bond angle of the carbon, and we can mostly have like 6, 7 member rings, 6, 8, even 8 member rings. So you can ultimately control also to how much disorderness you want in the material. So there also is a difference between the MAC and nanocrystalline. What interesting also in MAC also you see very small crystallites over here. So basically they are still crystallites, but they are like less than 1 nanometer size. So they are randomly distributed within the matrix of the completely disordered material. Because of this is totally disordered material, disordered one layer of carbon atoms, it has distortions. So based on distortions, you have different stain fields around it, and that also makes it a little thicker than graphene. So graphene is like theoretically it's 0.34 nanometer, or maybe let's say 0.4 nanometer, but in here it was around 0.6 nanometer because of that waviness in the material. But still, it will sustain itself. So most important for maybe you also as a membrane application, for example, mechanical properties are very important. And this is this is a theoretical study of that. So you can see graphene is more kind of brittle material. So it's sustained, the bonds are strong. Once you apply stress, it will keep stretching, but it will still elastically. But in terms of mech, you have kind of plasticity in the material as well. It has a little bit less strength as compared to graphene, but in terms of plasticity, is a higher plasticity. So it can be extended like up to 7%. Recently, there's a experimental paper on that one as well. So they also show that it has a very high fracture toughness, which is very unique in 2D materials. Like we can see compared with graphene as compared to meth, it has a very high fracture toughness. That is because of it's a random structure. So once you crack is just propagating through the material, it will change the directions because of these small crystallites there sitting there. So it will create some crack deflections, but that will absorb energy and your fracture toughness is increasing. So
ask a question, why can't you call these monolayer diamond and instead you call it amorphous carbon? You have got sp3 bonding, right? Mostly.
No, in this one we have sp2 bonding.
sp2.
That's the reason.
sp3.
Yes, it's mostly sp2 bonding. That's why we still call it graphite. You can maybe say like vaguely amorphous graphene. That's still fine. Yeah. Yeah.
Is it possible to have a powder?
In the powder form? You can, yeah, that's possible, but we haven't tried that one because for it likes to come from graphite to graphene, like in terms of vapor exfoliation. But in this case, I don't think it's very difficult to break the bond between the. So we haven't tried.
In general, when you are grown by CVD, we always from a lot of amorphous carbon.
Yeah.
Generally,
Yes.
we tend to avoid that as
Yes.
much as possible.
Yes.
But here you're able to control that growth as a single layer.
Yes.
That is the
the main point. Yeah, that's exactly right. I mean, there are a few papers in the previous studies also. There are always amorphous carbon there, and actually people wanted to get rid of that to have a very single crystalline. And even for this work, we started to aim. Our aim was to grow graphene, but we ended up to grow amorphous graphene. That becomes very useful in the end. So that was the trick behind that growth. This is the first time I was once we grow using laser CVD. That is very different from the thermal CVD technique. So in this case, normally thermal CVD process, we have high temperature, it dissociates and get new species. In this case, we use laser. So laser energy is basically breaking the bonds between the molecules. So in this case, we are not using high temperature to break the bonds. So laser, like a photolytic process happening to break the bond, and then on the surface, it will, once you have active species, that can deposit on the surface and create film on the surface. So basically,
You also have a plasma. You have plasma and
yes,
laser both together.
yeah. So in the next Wednesday, I will explain you. So actually, we can have both as a combination as a single only laser itself. But for the plasma, what does plasma do? Basically, actually, we got in 2024 LEAF grant on that. When we are actually building one of the this laser CVD tech setup there. So this is I just put for your interest as well. So how we can use it as a selected membranes. So because the theoretical papers also suggest that once you have these 8-member rings, like graphene has very high thermal barrier for the transport barrier for the ions. But once we have defects in it, it has enhanced its permeability for different ions. In this case, for example, for lithium, it lowers down to 3 or something, 1.3. So that's why we can use this material as a maybe membrane or sieve. Actually, we did one experiment. This is not by us, but one of the collaborating group. They did for the proton membrane as well as for the lithium ion membrane. So in that they tested and they see like it is quite high as compared to graphene. So both proton and lithium, but this is just for the one type of material. Of course, if we change the material, we can change the permeability based on that. And another one of example could be can be used also for the maybe as on an anode, a current collector as well can be used. There's one paper published last month, I think, in Advanced Material. They used MEC as on anode as well for the to suppress the dendrite formation. Another thing is also we can use it as in electronic devices. Normally, copper diffusion is one of the big problem. So copper can diffuse into the dielectrics and it shorts device. So we can use this kind of material as a barrier layer. So we can put it on the copper and then it will restrict any kind of copper diffusion into the device. So this is one of a project we also previously done with one of the NESTI partner. And that's all from my side. Somebody and I use synthesis as a toolbox to manipulate their properties, ultimately targeting different applications. We can target that one. And I will acknowledge my all teams like from Hong Kong to Singapore to RMIT and all the collaborators and funding agencies. Thank you so much. What for the time? 3 minutes for questions. Okay.
I was quickly ask a couple of questions.
Yes, sir.
Another meeting at 2.
Sure.
Oh, for another.
Uh, quick question. Quick question. If I remember it correctly, that when you did CVD graphene on copper, you used only argon as the carrier gas, no hydrogen. Is that right?
No,
You did use hydrogen for what purpose?
one, we also used to clean the copper at high temperature,
Mhm.
remove some of the oxidation of the copper surface,
Mhm.
make it more active, copper itself.
Yeah. And
Also, hydrogen helps to dehydrogenate CH4. Like it helps to create the first interaction where it creates like active species radicals.
Yeah.
So it helps to CH4 and to make it C2H5.
how about the copper surface? Does it have any oxide on that?
Normally, copper always have oxide. It's like so.
Not normally. It essentially will have oxide. because if you know Ellingham diagram,
Yes.
it will always have.
Yes.
So hydrogen will more importantly remove the oxide layer, and you will have catalytic surface available. Second question I have very quickly is that if I use plasma CVD, right, I do not have to worry about the catalytic action of the metal. Is that right?
Yeah. That's why we can lower down the temperature a little bit from 1000 to maybe 600.
No, my question is different. The purpose of copper or nickel substrate is to act as catalyst.
Yes.
To dissociate hydrocarbon into carbon and hydrogen.
Yeah.
If that dissociation happens because of laser or plasma, then I don't have to worry about what the substrate will be. I don't have to use catalytic substrate. Yeah,
Yes.
good. Yeah, thank you.
Thanks so much. Thank you so much. Thanks for guiding. Thanks.
Yeah, thanks, Irfan. Very interesting, especially that match material. Have you explored electrocatalytic behavior of this material? Because normally, like kind of amorphous material, at least in the context of metal oxide, metal sulfide, normally people are looking for amorphous or short range or defective, which I wonder maybe the mix phase is better like than the MAC itself. Have you explored?
You're absolutely right. We actually submitted one proposal on that.
Oh,
And that is true because disordered center always have higher entropy because of high entropy.
Yeah. Uncoordinated,
So definitely because this is totally disordered structure, and also you can see in the one of the simulation you also see there's like strain fields there, which actually are surface, high surface energy there. So that's always be very useful for catalytic applications. So, but there's not yet done on the because still this material is in the synthesis phase. So still a lot of paper are coming into synthesis, like because this one was done with the laser CVD. Now people are trying to do plasma enhanced CVD and other CVD processes. So still they are focusing on the synthesis.
Yeah.
In terms of application, there are a lot of application can be done.
Yeah.
So just very good question.
I think this is interesting material in terms of defect generation and defect control. How much degree of control you have on the type and proportion of defects, right? You can have say 7-membered rings, you can have 8-membered rings, 10-membered rings. So I need to what is the variation of the defects and what sort of distribution we can think about or you feel like we have a control over?
Honestly, at the moment, it's like kind of infinity to my mind because you can have maybe a lot of different defects, atomic lengths defects.
Yes, I'm talking about, yeah.
So we can have a lot of combination there, like we can change based on the conditions you're growing. So you can change the completely distribution of the defects. So there could be ranges, but what is specific structure is very hard to say.
So maybe then there needs to be a computational work done, right?
Yes.
To find out, say, in a structure,
Yes.
what sort of, because it's not trivial to have 8, 10, 15-membered rings, right?
Yeah.
And yet maintain your monolayer structure.
Yeah.
So there has to be some sort of computational, I guess, basis behind it. Yeah.
Yes.
Yeah.
The problem is it's very hard to simulate even amorphous structure. For crystalline, it's very easy. Once you talk about people with simulation, you don't have
You don't have inward cell. It's like glass.
So that's the most
Yes.
So even from where you start as a simulation modeling, it also depends like what kind of degree of disorder you want, and then you relax it, the structure ultimately becomes maybe different.
Correct.
So that's why.
So there's an open question, I guess, to.
I have a kind of question connected to my next one.
Yeah, sure.
Talking about control over the defects, have you a resolution over radiative and non-radiative defects? Because you're working on optoelectronic applications, right? Sometimes PL is quenchy, means that you don't have radiative, but you have non-radiative, which is more harmful because it gets like they generates heat, right?
Right.
Have you controlled or explored this effect in your defects? Generally, the defect methods that you're.
That's what we did. So basically, we wanted to have the thing is once you have radiative effect, basically you have higher PL. But in that, the nature used a low pressure sealing technique. In that case, we have higher defects, which is basically make it non-radiative emissions.
Yeah.
That's somehow useful in optoelectronic like photo response application.
Yeah,
So
how
these
about
are-
heat generations?
Heat generation I haven't tried,
Uh-huh.
but yeah, the defects can be very useful. You see, we did piezoelectric, we did electrocatalyst, we did opto-electronics, and the other things you can also explore as well.
Yeah, nice. Many things to explore.
Yes, thanks.
Hi, Irfan. Thanks for the wonderful presentation. I have a question. Is it possible to make monolayer amorphous TMDs or maybe MOS2 or something? Because it looked like a very interesting material.
Right proposal on this, like so, but that proposal we wrote it once I was in Singapore. So that was the first question, of course, comes into mind. So because this is the only carbon amorphous, how we can expand this amorphous family into like amorphous TMD, the amorphous boronite is very interesting. So the amorphous MOS2 electrochemical properties would be very interesting. That's what we were like thinking. So yes, there's possibility, but definitely it requires time and synthesis, recipes and everything. Yeah. But would be
Thank
very
you.
interesting. Yeah. This was the easiest one because this is just a monoatomic like carbon.
Right.
But
Yeah.
once you go to like biatomic, like boron nitride, like MOS2, so they have become more difficult, become more messy.
Right.
So then this is the one question. But it's what is when you make this discovery of monolayer carbon? Of this monolayer carbon material, and you mentioned that it was serendipitous, it was kind of accidental discovery, right? But then after that, what do you think were the most important parameters in your synthesis procedure that allowed you to get to a product like a monolayer amorphous carbon?
So it was how we can split these two things. One is because of dissociation, another is film formation.
Correct.
In thermal CVD, this thing comes together.
Correct.
High temperature cannot control dissociation happening on the surface, high diffusivity, and then rearrange itself to become the most stable structure, which is crystalline structure. But in the other technique, we remove that two things, split two
Correct.
parts. So one is precursor dissociation,
Yeah.
one is film formation.
Uh,
That
But I guess plasma enhanced CVD, this is
That
reasonably well known.
yes.
You can can segregate these two. But then how do you get to monolayer? Is there any other?
Laser itself, because how fast you retract the heat from the surface, that also helps. Like once on the surface, there's a temperature, there's no temperature available, so it's just kind of freezing. So there are like atoms that is freezing on top of it. But if you get a little bit, that's why once I show you the other different graph where we change the temperature, it will transform back into crystalline one.
Right.
From nanocrystalline one.
So then in this case, what is the temperature of deposition? It must be.
Normally in our case was around less than 300.
Right.
So dissociation comes from laser,
Yes.
then you are controlling overheating, right?
Yeah. Thank you so much.
Sorry, I just have a random question. I noticed you synthesized like bulk MOS2, which you use for like the painting experiment.
Yeah.
Yeah, so I'm just a bit curious. How did you do that? Because I noticed we've been working on monolayer material synthesis. So how did you make the bulk material? Okay.
What we like not a monolayer MOS, so that was different.
Okay.
But principally MOS to the same, so we use the same property into that one.
Okay. Yeah. Thank you.
Thanks so much.
Yeah, we had one question online, and this will have to be our last question because we've run out of time. So this is from Justin online. Considering the high production cost of graphene, is CVD a viable method for scalable and cost-effective graphene synthesis?
Yeah, that is very important question. That's what one of the also put it there as one of the drawback of CVD as well. So that's the reality. CVD at the moment is the most like people have been knowing CVD as one potential candidate for the scalable growth. But this is the main thing: the high temperature, and also CVD normally takes longer time. So it's like energy is not efficiently a process. So that's why we're trying to create some processes which has lesser temperature, and it can be like laser CVD is just quick, like just flash it and just get the film. So these kind of processes we have to develop if we want to move into industry and make it compatible. Yeah. Thank you.
Thank you, everyone. And thank you to our speaker one more time. Thank you, Irfan.
Thank you so much.